thinly populated or mediumly populated today, which is okay. So did most people have a chance to go through the slides that I shared yesterday? They were request to share the slides. And I'm going to try something new today. Let's try something technologically new. I'm going to try to write on the slides. Let's see if that works. Okay, though my handwriting is not the best, but hopefully that will kind of ease things up a little bit. Okay? Alright. So what we have, please settle down. Alright. So we have looked at since the binomial distribution. I don't want you to, get to the depth of it. Some people have asked for the full derivation of binomial going to Gaussian. I'm happy to share those rigorous derivations if you wish. Yeah, I just want you to take care of the notation. Okay? The only thing that I require from you at this stage is to understand what N is, what S is, what capital N is. That's one. Okay? And this is N combination small n. This part you understand, right? And how the powers are raised. I don't need you to understand anything else at this stage. Okay? At least in a preliminary biophysics class. So, again, there were questions outside. What we are defining as success and failure is upon us. You can call it pass, no pass. You can call it left, right, whatever. Doesn't matter. It's a binary choice. And at least in this example, we have called it success and failure. It could be something else as well. Does not matter. Alright? So don't take this success and failure very deeply. Okay, it's just a binary choice between two possibilities. Okay? So hence I said pay attention to the notation. Okay. Now, I hope this works. This does not work. And we are too far away. Sorry. So then we did this again, and there were certain questions as to how this formula came about. Okay. So if you pay attention, NA, okay, is the probability of taking small n number of steps to the right. The way I have defined it, I have set the coordinate system in a one-dimensional system at x equal to 0. If I take small n number of steps to the right, I will be moving forward by NA. Okay? And my probability of moving forward to the right by NA is is just the opposite. If I'm going right, I'm not going left. Hence this argument. Hence there's a minus n minus a times a. It's simple. Let's not make it overly complicated. Just understand where this is. And then we have put the binomial formula, and what I have avoided doing here, again, this is some amount of derivation. You will have to use the Stirling's approximation, so on to that. We are skipping that. But at the end of the day, you get something like this. Let's hope this works. Yes.
This will come directly. This result will come directly because 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 we did it in the probability statistic. So if it's a
So you can directly write this without any trouble. Fantastic. If you can, then that's the issue. I can discuss that with you. Maybe I have not looked over it, but if you can derive, how many of you think you can, what I've written as skipping steps, how many of you think you can directly manage it? Just raise your hand. So some people can manage it. Feel free to just write to me. So great. So, but since I gave it that way, I'm not going to seek steps from you. But the point is, when we have this P here, okay, if P is half, this becomes 0. So if it's a truly unbiased walk on the right or the left, it's a random walk. So you can think of this as a truly random walk. P equal to 0.5 truly, I'm putting random walk. Okay? You realize that? If that is the case, then your mean distance cover is 0. And we can make a simpler argument. Okay? I hope you got a chance to look through this derivation, again, it's quite straightforward. Kn is just the prefactor of A. It is either +1 or -1. Okay. And the average of Kn has to be 0 if it's truly random. Again, we are talking of, okay, so this is only going to be very or fully random walk. Now, and then you do this in an inductive fashion. You put the previous step, okay, and you can get to 0. So the next part that I've also shared, but if you do the squared distance rule, okay, why is this part equal to 0? Because again, Kn average, that's going to, Kn is a constant. I'm going to take that down and, that average of that will be 0. You can work out the steps. I put that as a little homework or as a practice problem. You simply work out the steps. Yes.
I just have a small question.
Yes.
So, when you see truly random walk, P can have many values, right? P can have more values, 6. So,
No, that's exactly what I'm not saying. So think of a linear random walk. You're constrained to walk on a line. Okay? And it's like just imagine one kind of a straight line with uniform points, grids. It's a long ruler maybe. And you can only make, say, 5 centimeter steps. Okay? To the left, to the right. So that 5 centimeter is constrained. And you can only go to the left or to the right. So if I put you or a tiny version of you over there, and I tell you you're truly random, which means that your choice to the left or to the right is random. It's like a coin toss.
So the way I was imagining it, okay, so I was imagining it, if it's truly random, then my probability of this will
No, see, that's the if it's truly random, then the probability of all choices are equal.
But the choices are two, going to the left and going to the right.
So in this case, since the choices sum up to 1, it has to be 0.5. It's just like a coin toss. Okay? Yeah. Yeah, because I'm taking the case that K and A is the displacement of the inner slit. Yeah.
But in the previous time,
Yeah. A K and square average will be 1. That part is clear.
That's a time versus displacement.
And has the time versus displacement thing.
Here, you get plus 2a plus
No, so this is a slightly different form. It's voiced down to the same thing.
Right.
I'm kind of redrawing that schematic in a slightly different way. Where I start from this origin, and by time I mean the time is progressing. We begin time later on. So if you wish, you can ignore this time part over here.
What I'm saying is in a single cell, you have 18 plus 2.
Okay, let me clarify. So I can read how this. Just imagine this as a coordinate system. Okay, so so just imagine this. Unfortunately, my pen will only work with red. This is a coordinate system. Okay, so this is plus A. This is where you end up with. Got it? And this is where you end up with if you go to the left side. Hence, I'll put this as grid in the background. These are the final positions. Okay, so it's essentially the same thing, written in a slightly different way. This part, if you want, you can ignore time in this slide with this. Of course, we have to progress in time, right? Alright, so these are not 24 that you just have to sit down and, in these. And what I would really like you to understand is when you go to a 3D random walk, something like this, again, the Rn square, if I have taken capital N number of steps, starting from some origin. So again, you can designate an origin here. Okay, presumably, so there's you have to start with respect to some origin. So imagine, the origin is here, okay, or, it could be, so this is some kind of this I think is the result of a real computer simulation. You can write codes. Those of you who enjoy coding, you can write this kind of a code where you make how to invoke random numbers, right? You have been taught, like, zero. So you make a random number choice and you make X or a Y or a Z movement in random numbers, right? And you keep doing it for many, many, many steps, and then find the mean distance, plot a distribution of the distance cover, plot a distribution of the distance square cover. Okay, that will be an interesting exercise if you wish to do it. But here, essentially what happens is, so this part would be, y n minus 1 square plus, this term will again come in, a square, and this is for the z term. So essentially, I'm going to group this term, and another one. Okay. So this should be Rn minus 1 square plus 3a square. And if I keep repeating, don't worry, I'll share these slides. Okay. So if you keep doing it, okay, I should end up with R0 square, that's the origin, plus 3 times capital N A square. Right? R0 is the origin, so you can ignore it. So how much distance square have you moved? That is 3n square. Okay, it's just a matter of, working out the algebra. What could be a little confusing is how you choose your coordinate system. This is okay. And what we did was we defined the diffusion coefficient in this way. I'm saying step square by 2 times time step. An approximation here again, a convenient approximation. I completely admit that we are using mathematics as a tool. Okay? To kind of develop the understanding. Okay, that could be, you could do it with a much more complicated mathematics. Those who are comfortable, we are welcome to do it. But we'll keep the maths simple. Okay? So and one question is why 2 tau? So, that is, you can take it with a pinch of salt, but we're doing squared displacement, so hence we use 2 tau. So if we do this, for a 2-dimensional system, we get Rn square equal to 4 times d is the diffusion coefficient. We have defined diffusion coefficient. We have at the outset defined diffusion coefficient as square of the step length divided by 2 times the time taken for each step. If I do that definition, this is what I get for 2 dimensions. How that 4 comes, and if you have 3 dimensions, it will be 6 degree. Okay, and then you can generalize it to this formula. This is the formula you've been taught in your practical class also. And there are questions as to, when should we think of it as a linear diffusion, when we should think of it as a 3D diffusion, so on and so forth. Those are very pertinent questions. I can share with you some situations where we treat V as fractional. V is, not linear, not, it's not 1 dimension, 2 dimension, there are fractions. Those are very complicated cases. But for now, we'll just take Cartesian diffusion and just treat d, small d equal to 1 or 2 or 3. Okay? Alright. So, then what we again introduced is this relationship. Okay? And, if you wish, we can maybe look a little bit more into this. So this is the result associated with, again, with something known as fluctuation dissipation. It's actually it's called a theorem, but it's not, so whenever you have a process which is dissipative, okay, it is associated with the fluctuations also. But I'm just putting the name here. Okay, this, there are in this class we pull up many things which are kind of connected to much deeper things, but at the end of the day, you see that viscous slows you down, so it is dissipated, and diffusion is trying to walk you through, right? Given your conditions, given your mass, given your size, you're trying to walk through. Viscosity is slowing you down, right? The product of this two is, what is KT? What is on the right side? The extent of thermal energy available to you. All right. So again, I hope some of you will realize that I can put RT also here. But then I have to put my, there are molar units of viscous friction coefficient and all this. So a quick exercise, just make a note, just go through the dimensionality of this. When I have KT, the right side are, what are the right side dimensions? Energy, right? L square to the power minus 2. So, and diffusion is L square to the power minus 1.
L square D1.
So hence you can look at the units of the viscous friction coefficient. It's trivial to then write the SI units also. This viscous friction coefficient can be written in terms of the viscosity. This is strictly speaking, okay, strictly for a spherical particle. If you don't write A, you can use something else. Don't confuse this A with the time step. If you want, you can use B. It's up to you. So this is strictly for a spherical particle, okay? But you're just going to assume that our particles are near spheres. So when I say a protein of a certain radius, okay, I'm assuming it's a sphere. So this strictly holds for a sphere, but nonetheless, we are going to use this relationship to, if the diffusion coefficient is supplied to us, okay, then we can do the viscosity, or the viscosity is supplied to us. If we know the temperature, we can get D. Yeah, from D, we can have some estimate of the movement of the particle, of the squared movement of the particle. Okay. All right. So another analogy is, and it's important to know this, is how many of you have heard of this particular database? Some of you. I presume those of you who are going and attending a few lab meetings or out of your own curiosity, this. There are databases of protein structures. There are other databases as well. You have databases of chemical crystal structures, so on and so forth. Okay. Nowadays, there's so much data out there. So the protein database contains the coordinates of every atom in a given protein. Yeah, maybe except the hydrogen atom. That is not always possible to come up with. But these are mostly experimental protein structures. Okay. But I just want to tell you that now this database is growing very fast, or growing to go even faster, because we have recently figured out in the last 10 years or so that you can bypass experiments also. Okay, you can bypass experiments and predict protein structures. Okay. And then there are complementary structures, part experimental, part, part prediction, so on and so on. Now, so if you have, say, a structure of a protein, there are two things to look at. Yeah. So again, I told you I'll come back to this. If you look at the end-to-end distance, remember I have a schematic of a, if this is my protein, this end-to-end distance, you can call it R end to end. This is a measurable quantity. Okay? And, there are polymer physics which shows us that this end-to-end distance is connected to the overall size. So when I look at this information, my end-to-end distance looks like a bell-shaped curve. The dot points are actual data done from measurements. And it has been shown that, these dot points correspond to a binomial distribution, a dual choice. And, it fits to a Gaussian distribution. But where does this all come from? So, stepping back a little bit, I know you might sound that I'm going a little bit back and forth, but have some patience. When you talk of protein structures, what are we talking about? What is a protein, by the way? What is, combinations of amino acids? Yes, absolutely. Anything, any other definition?
Peptide bonds.
It's a huge molecule at the end of the day, right? So you have these chemical bonds, you have, it's not a simple molecule, it's a very, very complex molecule, right? At the end of the day, you have the same thing. It's a very complex organic molecule, right? So inside a protein, you have this fine structure where you have these chemical bonds, okay? And these bond strengths are just written in those and, electron volts and so forth. But, 200 to, they're 100 to 1,000 times stronger than the KT that you have. Your KT is 0.6 kcal. These are way, way stronger, which means that, simple thermal energy cannot disrupt the bonds. You have to take, you have to increase the energy a lot more. But since these guys are there, we also have a gross structure. Okay. So in principle, you have to look at two considerations. On one hand, you have to look at that fine structure that will give you your Ramachandran plot, that will give you, how strong your peptide bond is. Okay. All those kinds of things, why is, what is the dissociation constant if you replace, so on and so forth. But you can also think of it as what is referred to as a freely jointed chain. Okay. So these are freely jointed chains and I can have segments here. Okay. And each of these are joined by something of, here I'm going to call it A. I apologize for my poor handwriting, but imagine this is A. Now, here I'm going to take a slight leap and say that all my A's are equal. There's some variation that I'll take, but no, it's not going to deviate too much from the average A. So if that is the case, okay, and this quantity, I think people were asking me earlier, is something known as persistence length. If any of you get very interested in polymer physics, there are exact definitions of persistence length, derivations, so on and so forth. So I think in the physics, biophysics, they teach all these in a little bit more detail. I think Gumi ma'am teaches that.
What was really joined together? This really joined.
I'll show. I'll show you exactly what this is. So what I'm trying to tell you is, this is again a DNA that has been treated as a freely jointed chain. So here you go. Okay. So if you have a one-dimensional freely jointed chain, it can either go right or left. Okay. And this is exactly what it looks like. So does this remind you of the first picture we had? Plus A minus A kind of thing. So again, binary choices. Okay, your freely jointed chain is either going this way or this way. Okay, you can extend it to 2D arguments, 3D arguments. So it's just another layer of mathematical complexity. What works very well in biophysics is to build up the simplest model and then add complexity. We refer to it as bottoms up. Okay, top down, you overly complicate things and then you break it up. That's also possible, but the more popular way to do is bottoms up. But at the end of the day, folding has some similarities to a diffusive process. Okay, so the protein folding, maybe we can do a special lecture on protein folding outside the syllabus, time permitting. But this folding idea, it's a very complex process, but part of it is this diffusive search, random search, okay, for the right configurations. And a signature of that is this end-to-end distance. Okay, this is how much I'm going to extend it to. So the reason for looking at diffusion is many. I shared 3 or 4 examples yesterday, even bacterial growth colonies and so forth. But there are many reasons to understand diffusion in biology. And if you understand that random walk model, that gives you quite a bit of a head start. There are also things like it might sound a bit anomalous, people also talk of biased random walk, which means that, something has been added so that it's not exactly 50-50. Okay, there's a interaction. So even though it's it looks like an isotropic plane, but maybe one wall is a little bit rough. Okay, or there's some interaction which is slightly different from the others. So, I can redistribute the probabilities in a way. These models are all there. Yeah? Okay, so let us move on. So what we are going to now talk about is now go back and think about your potassium permanganate experiment, which you did in your 2102, right? What did you see? You had KMNO4 somewhere. I have not. It's a new experiment for this year, so I've not done it myself. Maybe next year I will. But you put some KMNO4. It takes time to reproduce, right? If you were to use a slightly warm water, if you take some warm water in your flask, maybe you can add a little bit warm water, and if you take a stopwatch or something and look at the distance while it's the highest in density has moved, it'll be a bit faster, right? That you can bring up. Now, so what we are going to talk about is something known as flux. This is a new word that I'm talking about. By definition, it's a simple thing to think about. We are going to talk of movement of particles through per unit area, per unit time. Particles, so if I have a wall, say, let's think of that door, and each of you is a particle. So, when the class ends, I have some of the TAs do this exercise over 10 days. And I see that within a time span of 3 minutes, how many students are working on. Some might be trying to come in as well. If I don't distinguish you with the next class, there will be a flow, right? There will be a, exchange. But at the end of the day, how many are working out from this end to the other end per 3 minutes? So that is the number per unit time, per unit area. We will need the area of the door. Okay, so that is exactly what flux is. So by that started, what are the units of flux? It's per unit area, per unit time. Tell me the dimensions at least. L to the power minus 2, t to the power minus 1. Right? Now do your SF. For those of you who may. Now let us look at this example. So, this movie kind of will remind you of the diffusive process. But think of these 3 planes. And think of coordinate system, a Cartesian coordinate system. What has been done is these planes have been placed along the x-axis. Okay? So I have this plane placed at x. And I'm going to place another plate also on the x-axis at x minus l. If I do that, I'm also assuming that the concentration around y and z is invariant. Does not be. So the number of particles crossing overall, number of particles overall, crossing from left to right will be the number of particles here minus the number of particles here. I'm going to do a half because, I'm going to assume that the same numbers are moving in both directions. Okay? And let me now divide this number by L. Okay, so this is a separate exercise you might think of. If I divide this by L and I make my L infinitesimally small, what have I ended up getting? I have ended up getting minus dn by dx. Okay, why minus? Because my coordinate system starts on the left side. Okay? Now, I'm introducing another quantity called C of x. Can anybody guess what C of x is? It is the concentration at position x. Concentration, the unit for number concentration? Number per minute volume. Concentration is typically, unless it's specified in a different way, it is something per unit volume. The C of x is a number concentration. Okay? So when I want to find the number n, I'm going to multiply concentration by volume. So then y into z into this L. And next, if I transport it over here, okay, this algebra can be worked out simply from here. Okay, y, z, L squared, just a moment. So when I simply, just take this and transport it here, we are going to get minus yz L squared by 2 dx of concentration. Okay, and again, I'm going to define flux in this way. So this is my flux. Again, work out the algebra, okay? So flux has already been called J. So this is your flux. Okay. So can you observe all of this and tell me what will be the flux? I'll give you one hint. I'm going to say D. From, if you focus on this equation, how should I write my D? Remember how I had defined my diffusion coefficient before? Huh? No. How did I define D in the first place? Right. So here, what should I do? Okay. So if I do that, I'm going to end up with this equation, which is actually a very, we kind of did it in an overly simplistic fashion, but you're going to end up with something which is the fixed law. So if I have a concentration gradient, what do I mean by concentration gradient? A spatial change in concentration. So you can do a space derivative of the concentration. If you're able to do this, the flux will be proportional to the space derivative of the concentration, and the proportionality constant will be minus D. Is that okay? Hence the minus D.
So in that case, we did half of one. We did half because it's going on both sides.
Overall, very pertinent question. Again, we are arguing that the spacing between them is infinitesimally small. Got it? So then we actually retroactively L tending to 0. That's a good question. We are assuming that, it is so tiny that, it does not change much. So hence we, there are again more rigorous definitions. If you can actually derive it in a more rigorous way. Yeah. No? Yeah. So you see those two planes here? You see this plane to this plane, right? And you see there's a greater concentration here, and the concentration is decreasing here, right? So, you can imagine that my particles will go this way. Okay, so again, left is, as I gave the analogy, I have my door, I have students moving from left to right and some coming out from right to left. Okay, but given that, as she asked, why that half factor, you can assume that, some of them are kind of crossing each other in that manner, and my space within which I'm measuring it is infinitesimally small, L tending to 0. Okay, hence I will justify that half factor. Yes. I hope nobody thought this is n times exponential. This is yes. Is that a confusion? This is n x minus L. N have the position. And hence this is n and x. Is that clear?
I'm just guessing number 5 here. Why do I get number 5?
Yeah, that is the difference, right? So that, given your consideration of time, will go from one end to the other. So, we know that there is a movement of particles. So, how many are moving? Infinitesimally small distance I'm trying to find. The movement, right?
Here also, I think the very random one.
Hmm?
So
It is a random walk.
the probability of going forward is 1.2 and backward is also 1.2. And the minus stuff gives us the first one.
Minus comes exactly. So what you just said, there's a little bit more woven into this. We are running a bit late, but still I'll tell you something. I think Vidisha has also said this to you because she and I had a discussion. When you think of in our childhood, we have been taught that, things diffuse from one end to the other. If I spray some perfume here, 6 meters from here, you will get it after some time. It is not that all the particles are, forcibly going to that. If there are a few molecules there as well, that is also moving. It is just the overall randomness. Nothing is preventing one molecule at that 6 meters away. Let's say we take a spray bottle and you spray something, low concentration, and I press it, say 10 times. You press it maybe less than one time, half a time. Those molecules are also coming here. It's not that the mean square displacement of the molecule I'm spraying, if they are the same molecules and the one that you are spraying are different. It is just that overall there's going to be a movement, but it's just simply more number of particles moving outside. But the D for that one and D for this one are not different. It is just the numbers which make it seem, and people make that confusion that it is just going more on that side because there are more. It's just the numbers. But the diffusivity of individual particles remains the same. Okay. So this is a very useful equation. Okay. And this is known as Fick's law. The other thing is how this, again, we are not going to show. I'm not looking at I'm going to skip the proof, but it can be shown that the time derivative of concentration equals the space derivative of flux. Okay? Concentration by itself is only a function of position. Okay, position, there is also implicitly a time. You can write this as partial derivatives as well. If you want, you can write it. If you want, you can write it as partial derivatives also. If I substitute this equation here, I'm going to get this very useful equation, which is known as Higgs diffusion equation. What have I now skipped off here? What is gone in Higgs diffusion equation? The flux side here is gone, right? Now I'm only going to deal with concentration. Concentration is a greater measurable than your flux. Okay? So I only have concentration, okay, function of space and time, diffusivity, again a measurable quantity, and I have a neat relationship between it. Now the good thing is, you see there's a second derivative of concentration. Just can anybody remind me when I do a second derivative in space, what is it usually referred to? You find the maxima and minimum, but also first derivative is slow. Radius of curvature. Okay. So the first derivative gives you, the stationary points, and the second derivative will give you maximum or minimum. But the second derivative, when I have some kind of a curve, will give me something known as curvature, as we said. And if the second derivative changes, okay, the second derivative is not a constant. I'm not even talking of plus or minus. I'm saying that the second derivative is changing. What does it give me? It gives you inflection point. Change in the second derivative, right? So if you have something like this, if I have No, there are there will be points where this itself these are known as inflection points. Now let us look at it from that perspective. And by the way, these examples are so this is the curvature of the concentration profile. So let's say, I have an initial concentration. So this is initial concentration profile. Let's say this is the initial. So after some time passes, what is the behavior of this part? If I have concentration as a function of x, uniform concentration in my direction of interest. It should be 0. Even del C del X is 0, right? So, just like in this room, just imagine in this room we have concentration of oxygen which is not changing. If I don't do anything, nothing will change. It will remain the same, right? But let's say I have this kind of a profile where I have a high concentration of my favorite perfume here and it goes down. How will the concentration profile change in time? What is del to C del X squared here? That is also 0. Okay? So del C del T, this will not change much in time, but if you have another scenario, this is a very common scenario. Where you have, and this is very common, especially in biology, where you have, say, a burst of nutrients. Okay? Or you have a burst of, say, toxic chemicals which are released. Okay? By an organism or something. Okay? And it assumes a bell-shaped curve. Let's assume it's a normal distribution of those concentrations. How is that concentration gradient going to evolve over time? That is something that will pick up a few more problems based on this idea. How is it going to change in time? So what I have marked and what the textbook has also marked with these stars are these are the inflection points where your curvature itself is changing. Okay. So at these points, you see, the profile is going to change. The concentration will change very sharply at these points. Okay, so this is, you can think of this as the original profile. Yeah, no, we are looking at the left side. How will the right side determine the left side? What is said here is that the concentration, look here. If dC by dt is negative, which means the concentration will go down in line. Okay. And if your right side is positive, the concentration will go up in time. So for a profile like this, in some places you will have a decrease in concentration, in some places you will have an increase in concentration. Does that make sense? It will depend on the local curvature of the concentration profile. The local curvature of the concentration profile is determining whether your local concentration will go up or go down. It's a very non-uniform profile, right? Now think of very complicated, relatively more complicated scenarios of an organism releasing some chemicals, bacteria kind of, at what rate, if there is nothing else at play, and you supply nutrients to a bacterial colony. Okay. And the other playing factors are minor, and this is the major. Concentration profile is the major playing factor. Can you determine in time how the concentration would look later? And how does that affect? So, how's that going to affect the bacterial growth following? How? So, the way you do things is, you take apart bits and pieces. Okay, you build up logic in a modular fashion. That's what I can tell you. If you decide to work on problems of this kind, instead of building one very complicated equation with many things involved, it's a better idea to build it in the modular fashion. Okay. So we'll pull up a few more examples of how concentration profiles can be altered when you employ the fixed diffusion equation. Okay. Acha, yes.
Here there is a baby, but the derivative would say like there is no view.
No. So there is a gradient, but there is no curvature. Right? It's a same slope. There's no curvature. So the second derivative in space is 0. Okay. Which would suggest that the concentration in time. I see your conundrum as to why this will remain at high concentrations only. Something which does not seem intuitive, right? That's what you say, that, this mathematically fits. But if I really have concentration profile with this crashing, think about it a little bit. I understand your conundrum. That does not make intuitive sense. That if I have a concentration profile is very sharp here, why would the other particles not diffuse on this side? These are all hypothetical cells. But that, but accident resolution was there. Let's discuss this case a little bit more. Okay, just think about it. Why is your physical intuition inconsistent, apparently inconsistent with what the equation says? Yes.
Why are the assumptions made look very reality?
I want to hear from you. What is the fundamental assumption here?
There's no decision, but
let's do, what are the fundamental assumptions here? The very fundamental assumption is there's no external force at play. But whatever we have is at equilibrium. Nothing else. We will come to it later in the class, where you can offset diffusion by external factors, such as you can have gravity is a very weak force. You can have an electrostatic force, so on and so forth. So this equation is going to get modified now if these particles happen to be charged, and if I apply a delta V potential difference. That is the basic assumption. In fact, I think that is the only assumption.
Theoretically, this makes sense because this exact graph will only hold for t is equal to a specific time. So if t is a constant there, then naturally the expression c will
T is not constant. It will evolve inside, right?
it will evolve.
So this is say at t22. This is at initial time. So this will lead to what?
This should lead to the straight line.
Yeah, but what he is saying is, since the curvature is 0, then this should then del C del T should be equal to 0.
But actually, like c is a function of x and t. Then this graph is not showing us everything about because it's a function of two things. It's also showing it on it. That's why I think we are getting an incomplete information about this.
That's a good way of thinking about it. Now let's come back to this discussion a little bit more. I want to leave you some things to think about. But for other questions as well, who else had, I'll just take turns. Who else had raised their hands? If they still want to raise it, yeah.
Final confirmation to see the point, like, but the initial is a concept of happiness, take it to be a signal, it's going to be like,
Yes. Or it's so not if you wish. Yeah.
and the final, then the confirmation is you and the clear, let's see what
Single?
that one of those things now, you look for things that, what is it? Yeah.
Oh, so that is at x equal to 0. Whatever my choice of coordinate system.
Y coordinate is greater than other.
Huh?
So y coordinate.
You are not considering y half.
Alright. The constellation is completely my coordinate is when in constellation is greater than the US particular move communication.
Okay, fine. In the flexible and force.
Initially, there were
These are three different scenarios. The three problems that I showed you. First one that I showed you, that is a case A, this is case B, and so don't connect, this is a case C. Okay.
so this is the point, this is not point.
No, so this is that initial, this is that time t equal to 0. After time, after some time, what will it go? That is the question I'm posing. I'll put it down. Yeah, but as he pointed out, it's very counterintuitive, right? If I have a high concentration of molecules, that's kind of hard to let's say a 6 time, right? It doesn't have to go. Okay. And I have a high concentration and a low concentration in space. Let's say within a span of a meter, I have very high concentration of some gas, very low. So if I get time at all, this whole thing should homogeneize. Yes, that is the argument we used for this equation. But then, no. But if I let time flow, then shouldn't I expect homogenization? Is what my intuition does. But this is a little bit which is looks apparently inconsistent with this. So let us try to look at the ultimate solution after time, after resource.
Absolutely make a third life for the
You can do that.
and then it will slowly become as the time progresses, it will slowly become the
So let me leave that as a coding problem. Those of you who kind of get enjoyment out of writing these things, you are welcome to try these up. These are not, you can do it on your laptop also. All right, we need to close here. Just quick point. So, today evening we'll show you the answer sheets. Next week, I actually have to travel for a couple of conferences, so Bidisha ma'am will take your classes, okay? She'll do a little bit of discussion on diffusion itself, and there may or may not be a test. It's always may or may not be. I want you to be prepared. It's not complicated. If you have studied what has been discussed in class, you are in good shape. If you have studied what is discussed in class, you are in good shape. So, when you've gone